Here's a solution for day 4, problem 1. Sketch the graph of f of x equals sine x. We want to graph this trigonometric function. The way that you can graph any function is to choose numbers to put in for x and then find the corresponding function value. That gets you ordered pairs where you can put the points. Now, when working with trig functions, it's helpful to choose easy numbers for x, numbers that you can find the sine value of without resorting to a calculator. Trig functions are related to the unit circle, which we looked at in a previous lesson. Recall that on the unit circle, there's a y-axis and an x-axis, and that it is a circle centered at the origin that touches 1 on the x-axis, touches 1 on the y-axis, -1 here, and -1 here. And that angles are created on this unit circle by starting along the x-axis and then swinging up in a counterclockwise direction a different amount of radians. The angle right here is a 0 radian angle. The angle up here, a 90-degree angle, is also called a pi/2 degree angle. Swinging 180 degrees around there is where pi radians is. Swinging 3/4 of the way around a full circle is 3 pi/2 radians. And going all the way around a circle back to 0 is 2 pi radians. Each of these points has an ordered pair. This is the point 1, 0. This one up here is the point 0, 1. This one here is the point -1, 0. And this one down here is the point 0, -1. There is a picture of a unit circle in the back cover of your pre-calculus book, which you might want to consult whenever working with trig functions. So one number that we should try for x is to try 0. When you look at this point on the unit circle, where a 0 radian angle would be located, its ordered pair is 1, 0. The sine function is the y-coordinate of that ordered pair, 0. So when x is 0, the function turns out to be 0. There is a dot at 0, 0. The next x value to try is pi/2, because it's very easy to get the y value for pi/2. It's 1. So when x is pi/2, y turns out to be 1. There's the dot. Another number to choose for x is pi. For a pi radian angle, the y value on the unit circle is 0. So when x is pi, y is 0. And here's the ordered pair, pi, 0. Next, let's go to where 3 pi/2 is located. Its y-coordinate is -1. So on the x-axis at 3 pi/2, y is -1. That's down here. Swinging all the way around the unit circle back to here is 2 pi radians, and the y value is 0. So when x is 2 pi, y is 0. This picture, when we connect the dots, represents one period of an infinitely long curve that is the sine function, sine x. This actually continues and replicates this pattern. So it would continue swinging up there, right, and then come down and swing up. It's called a wave curve. It also continues to the left. So if we were to locate some more dots to the left, we could show a bit more of the sine graph. So this would continue down here to get to the -1 level and then start to swing up, crossing through 0 here, and then it swings up here until it gets to a height of +1 and then starts to come back down like this. It has peaks and it has valleys. It is a wave function. Day 4, problem 2. Find the sum of the first 150 terms of this arithmetic sequence: 5, 16, 27, 38, 49, etc. An arithmetic sequence is a sequence of numbers that has a common difference between the terms. What is the difference from 5 to 16? That difference is 11. From 16 to 27, the difference is 11. From 27 to 38, the difference is 11, and so on. An arithmetic sequence is a sequence that always has the same difference between terms. We want to find the sum of the first 150 terms. Well, we don't want to actually write out all 150 terms and then add them together. We don't have that much time. So we want to use patterns or formulas to find the sum of the first 150 terms of this sequence. The formula that will work here is S for the word sum, sub n, where n represents how many terms we want to find the sum of. In this case, we're going to let n be 150. This is equal to n divided by 2 times the first term of the sequence. We're going to use the variables a sub 1 to represent the first term of the sequence, plus the last term of the sequence. We'll use the symbol a sub n to represent the last term of the sequence. In this case, n is going to be 150, the 150th term. This is a quick way to find the sum of numbers that are in a sequence. If you add the first and last numbers together of the sequence, and then multiply by half of the number of terms in the sequence, that finds you the sum of the numbers. In this problem, we want to find the sum of 150 terms. So n is 150. A sub 1 refers to the first term, which we can see is 5. A sub n refers to the 150th term. We don't know what that is because the original problem only lists 5 terms. We need to figure out what the 150th term is so that this math formula will find us the sum. To find the 150th term, it would help if we had a formula that could find us any general term we were interested in. So let's make a formula that finds any term of this sequence. The common difference between terms is 11. We could also call that the rate of change between terms. So we can use our basic slope-intercept form to create an equation that finds terms. The slope, or rate of change, is 11 times n, and then remember how the y-intercept would go here on the end of slope-intercept form? Is there any adjustment that needs to be made in order for this equation to actually correctly generate these terms? Let's say n is 1. 11 times 1 is 11, but the first term is really 5. So how do you adjust this in order to make it output 5? We would have to subtract 6. Let's test this formula on some of the other terms and make sure that it works. 11 times 2 is 22. 22 subtract 6 is 16. That is the second term. 11 times 3 is 33. 33 subtract 6 is 27. And that checks out and matches the third term. So this general formula seems to find us any term that we want in the sequence. We want to know the 150th term, where n is 150. So let's put in 150 for n and find the 150th number in that list of numbers. This makes 1,644. Now that we know the 150th term, we can put it into this formula we wanted to use earlier. So we have that the sum of 150 terms is equal to 150 divided by 2, which is 75, times 5 plus 1,644. If we work out this math, we will have the sum of 150 numbers in that sequence of numbers. This results in 123,675. Aren't you glad we didn't have to actually figure out all 150 numbers and then add them together? Look how large of an answer it turns out to be.